I'd like to thank Brad, Murat, and all the organizers for giving me an opportunity to speak. The point of my talk is that if we want to achieve orders of magnitude improvements in computational efficiency and get around Moore's law, I think the most important thing is actually how we represent the data in the hardware, even more so than the hardware itself. So, just move this up here. So, and in particular, I'll talk about the advantages of sparse distributed representation compared to localist representations. The original title, algorithmic parallelism, is really a synonym for distributed representation, if you think about it, and I'll explain that. So I'll explain the advantages of sparse distributed representations compared to localist, and in the process, I'll talk about machine parallelism as well, or compare it to machine parallelism. So we're all aware of what machine parallelism is. This is a very abstract view of it, in particular something like a CPU, GPU framework. So it's the idea that you have a whole problem, you break it up into pieces, you ship the pieces to individual computational elements, they do their work, and they send their outputs to a central point for combination. So, one of the important things about this, actually, wrong point. In the existing, machine parallelism paradigm, even if it's got CPUs and GPUs, within each of those units, there's still the processor memory distinction. And so the point of the animation I just did was to show that even if you bring the processor and memory, if you completely co-locate them, as for instance a memristor would do, you still have the machine parallelism paradigm per se, introduces the need to transfer data. And as most of the people in this room, I'm sure, are aware, transferring data back and forth, whether it's between a processor and memory locally or amongst nodes more globally, chews up most of the power and time of computations. And as an aside, or a note, we've been talking about convolutional nets. I think as many people will know, convolutional nets use tied parameters or shared parameters to greatly speed up their algorithms. And I would imagine that almost all of the convolutional net implementations that have achieved the great benchmarks that we've all seen use tied parameters. But tied parameters, that introduces a need to, computing these averages of gradients, introduces the need to ship a lot of data around. This was acknowledged by Jan LeCun at the deep learning tutorial in NIPS a few months ago. And there are some, I would say, fairly nascent solutions that he mentioned, but I think it's a serious thing to keep in mind, for the enterprise of designing, new hardware. So sparse distributed representations compared to localist representations. That terminology is probably not used by most hardware people, but localist representation simply means that each individual represented item in the system, whether it's a concept or an input or a hypothesis, is represented by a single unit. And a corollary of that is that a single algorithmic step or an atomic operation will update the state of only one unit. So in this little cartoon here, this is a localist representation with 6 items sitting in unique or individual memory slots. And if the atomic operation was increment, if you apply it to any one of those items, let's say 8, it's only going to operate on 9 because the units are physically disjoint from each other. So whatever you do to one unit, it's not going to do any work on any of the other represented items. So in contrast to distributed representation, the first 2 bullets sort of define it. Every represented item is represented by a set of coactive units in the coding field, and every representational unit participates in the representations of multiple items. And a corollary of that is that a single atomic operation on one representational unit will now update the state potentially of every represented item that uses that unit. And this is just an aside. Sparse distributed representation is not the same concept as sparse coding, so we can talk about that later, but just to disabuse or clarify, I suppose, at the outset. So this is a picture of one of the sparse distributed code, the sparse distributed architecture that I've been using in my models for since my thesis in the early 90s. And it's a sparse coding field consisting of 6 winner-take-all modules. A code will be a choice of 1 winner per module. So usually you have an input field connected to it, and if you apply like an input pattern, it consists of 5 units. You might pick that particular sparse code to represent it. You'd increase the weights between, and then these are several other choices that you could pick. Several other codes that you could pick in this representational field. And the point is a point is that this is an exponentially large code space, 3 to the 6th in this case. I want to point out that even though the code space is exponentially large, in practice, in operation, you will only ever be able to use a vanishingly small fraction of that code space, because the limiting factor in storing and retrieving, especially if you want to do best match retrieval, is the number of weights that, that impinge the coding field. So sparse codes, there's a natural similarity metric over codes. It's just the size of the intersection. And so reiterating the point there that a single atomic operation here updates the states of multiple items. So, I've shown 1 unit there with the red box around it that's shared by those 4 items stored in this memory. If I turn that item off, then I've updated or influenced this or affected the state of all those items that share it. And so in Sparse, in the models that I use, the coding field is going to be representing a likelihood distribution over stored items. And the measure of how likely an item will be the fraction of its representational units that are active at a given instance. So it's important to point out that if this particular code's active right now, code for A, let's say, well, then it's, the other items are physically also active to the extent that they overlap with A. So really, a sparse distributed code functions dually. It functions as a single most likely item. It also functions as a likelihood distribution or a similarity distribution over all the stored codes. So for such a scheme like this to work, you need to have an algorithm that when it stores new codes, it has to preserve similarity from the input space. Because only then, if I then turn off one of the units that's common amongst a bunch of several items, you need to preserve similarity so that the semantics of the domain being modeled are sort of respected by the code manipulation. So this is putting SDRs side by side with localism just to show that, so this has a consequence in terms of time and power. They both have fields of 18 units. But as I just said, you can add more codes to the SDR field. You're not going to get anywhere near the limit there, but you can add, let's say, 1 more, just notionally, and you don't have to increase the number of weights, right? So if your algorithm for updating the state of the entire distribution is dominated by a single iteration over the weights, which is the case in my model, then the runtime, as you add more and more items, as you store more, the time to update the distribution, which is it's called belief update in the Bayesian network literature, remains constant. Whereas if you have a localist model and you want to add 1 more unit, store 1 more item, you have to make it larger, you have to add the weights. So if you want to scale in general to larger data, you'd prefer a model that has this characteristic. So over here, I mean, in SDR, you're storing all your information in superposition. It's, as Penty said earlier, this is content addressable. The address and the content are munged, completely munged. You can't look at one representational unit and say that's address or that's content. They all function dually. So I've always made the allusion in my work or the correspondence of these SDR coding fields to the cortical macro column. So this is a picture of a notional macro column. And in particular, the codes in my models I propose correspond to the L23 population specifically, the pyramidals. And the picture up on the right there is from Clay Reed's lab from a while back, just to sort of suggest that that's a picture that's imaging in L2-3 of mouse cortex to suggest that something like this sparse coding format might be actually happening in macro-columnar containers. The codes turn on and off together, and I've described this in many places. Of course, the code space is probably something like 20 to the 70th, and if you believe the standard neuroscience literature about the rough size of a macro column and the rough size of a mini column. This is a picture. I'm not going to go into details here. This is in my papers. This is a picture of the circuit that does both the learning and the retrieval, the best match retrieval, and that has this characteristic of having a fixed time over the life of the system for storing more and more items. But this is all cast, and I won't go into these details. Questions offline if we want. So far, in the last 3 years, I've been supported by Dan under Upside Seedling. And I guess I lumped the results of the research into sort of two broad categories. So this is, I'm not much of an applications person, but this is what we've been doing. Applying Sparse, I'll show you the network in a second, to Wiesmann data. And I'm sorry, yeah, so far, right. So this is what the Wiesmann data looks like. There's 90 of these snippets. There's 10 different classes. We pre-process into just pixels, edge pixels. So this is what our learning inputs look like, and we decimate in time as well. So yeah, it's very simplified, or that we don't use SIFT or HOG or HOF or any more engineered features. So far, I think we're the only organization that I know of that's applying sparse distributed representations to benchmark video event recognition tasks, and the only ones I think to publish results of operational hierarchical SDRs. This is the same experiments capturing both bullets. So this is a picture of the network that that we applied to Wiesmann. And well, so just before I talk about that, the second main bullet for the results of the research is that we've really learned a lot about how to build these multi-level networks that consist of a lot of modules. Here, there's 216 of these MACs. You can't see the cells here. 54 at level 2, so this is a 3-level model. This is a Wiesmann snippet of a person doing a jumping jack. The cyan patches are the receptive fields leading to 4 of the MACs outlined in green. So on the first frame, 2 of them are active, and a MAC will become active if it meets a criterion in terms of the number of pixels that are active in its receptive field. And if it meets that criterion, it'll fire, it'll assign a code, and the weights will be increased and so forth. So this is all happening in parallel. That same circuit diagram I showed earlier runs on every frame in every MAC. The MACs at the top level have twice as long time constant. And if we go to higher levels, we kind of double the time constant so that you get sort of a chunking phenomenon that takes place and so forth. So what happens is every time as I move through here, even though I'm not showing you the codes, each successive code that's activated in a MAC really represents the spatio-temporal moment, the sequence of frames, and focused in the aperture of that receptive field that have occurred, leading up to the current event. So it's a variable Markov model, variable length Markov model capability in terms of these codes that are being stored. So, 67% kind of low. On the other hand, I actually went right past the bullet. I mean, the point is we do it in 3.5 minutes with no machine parallelism. And we just use raw pixels and so forth. We haven't done much software optimization as well. So the 3.5 minutes can actually get a lot faster and well. Right now we're engaged in this human-in-the-loop parameter optimization because there's a huge amount of hyperparameters here. The size of the receptive fields, the criteria you have to make MACs active, and they all depend on each other across as many levels as your network has. This is just another picture to show the same thing, but in plan view, and you can see the codes activating now. And so for our learning, what we do is on the last frame of a snippet, we take the whole vector of activity over the cells on the last frame, and we put them into an SVM to test the classification of the system. Don't worry about the color scheme right now. We use leave one out training and data augmentation too, rather modest data augmentation. And this is just a 3D view of it. But I don't know where I am on time. I got 10 minutes? Good, okay. So I wanted to just tie back to the point about likelihood distributions. So this picture shows, the same thing. This is a different snippet. This is a person bending down, and so I've highlighted one MAC here, and I'm showing its receptive field. And of course, the receptive fields of higher level MACs consist of integer numbers of MACs below them. So there's that cumulative fan in, fan out effect going up the levels. But so on the first frame here, so what I'm showing here is the result. This is a picture of a model that learned 3 Weisman snippets, total of 40 frames because we decimate. And on 30 of those frames, this particular MAC I've highlighted activated, and at that time it would have assigned a sparse distributed code to represent whatever spatio-temporal moment was present in its receptive field. And so what I'm showing here is the distribution of how active each of those stored codes is, which is basically a surrogate for a likelihood distribution in the current recognition moment. So. And the blue bar is the bar that we want to be maximal. This is 0 to 1. And so what I want to show you as you slide through here, this distribution sort of changes arbitrarily. It can change arbitrarily from one moment to the next as different information enters each MAC. By the way, each of these MACs is on every frame integrating the bottom up, the horizontal, and the top down input and doing a spatio-temporal match over that global input compared to all of the codes that have been stored in the past. So the bar sometimes, we want the blue bar, the dark blue bar, to be maximal, and when it's off, there's no codes in there, and it kind of marches across, and you get the idea. The same thing's happening at L2. Except that there's fewer codes stored because the persistence is longer for these codes, the time constant's twice as long. Okay, so this just embellishes it a little bit to show the actual spatio-temporal moments that correspond to these bars, to these stored codes. So, if I slide through here, on the very first recognition frame, the first blue bar corresponds to the code that would have been stored on the first recognition frame of this snippet during training. And so that's a spatial input. But if you move into it, you start to get these spatio-temporal moments, which I'm showing unfolded in time here. And again, it's just the information coming in the receptive field, that's seen by the MAC connected to that bar. And the same thing is happening up at L2 as well. Those unfolded sequences at the top come as doublets because they're on for 2 times in a row. There's lots of, I thought I'd go through this a lot more slowly, but there's a lot of questions, or there's numerous things I could talk about in terms of compositionality and so forth. I mean, everyone in deep learning and probably everybody in this field in general understands how essential hierarchical representation is. You get to reuse parts of parts and so forth, and so there's information compression in that. And compositionality is a huge topic that's embraced and used by basically everyone to the extent that they can. So, and it's present in this model here as well. It's just that the parts in my model are represented by these sparse distributed codes, not by singletons. So for instance, in every flavor of HMAX model I've seen, for instance, it's hierarchical, but they use localist fields at every level and at every location. They're all localist fields. There's one winner per field, per time step. So, well, that's just a contrast. Okay, so in summary, I mean, we've made much larger nets. Here's a guy reaching. This is from some Vihasi video data set. This is a person reaching. I think it's actually an animated character's outline. And I'm not publishing quantitative results on successive classification here, but just to show you the character of the model. We can build arbitrarily deep models, and there's just a million parameters: how big the winner-take-all modules are, how big the MACs are, the fan in, fan out, and all that stuff. So to summarize, I really think that how information is represented is not to be overlooked. In the design of the new generation of machines, I think it's you get a huge, I think probably exponential savings with respect to certain other algorithms. I mean, localist algorithms are ubiquitous. First of all the data on Earth, I would assume, or most of it, is stored in localistically. I mean, every Oracle database, records are stored, two different records are stored disjointly from each other. Two different fields within a record are stored disjointly. So all the data on Earth is stored localistically. And a great deal of the machine learning models, I mean, all the Bayesian nets, all the dynamic Bayesian nets, they assume localist representations. So I think I'm raising a point that I think is important in terms of achieving large increases in computational efficiency, both in time and power. Okay, so I guess I'm finished. So I'll take any questions.